Hello, everyone. My name is Michael Del Mastro. I am a master's student at the University of Ottawa here in Canada's capital. I'm part of the Lundin Lab, which is run by Professor Jeff Lundin. And for this project, we're working collaboratively with the Boyd Group run by Professor Robert Boyd. So when you think of compressing an optical system, you can think of metalenses. When they were first demonstrated in 2012, they were low efficiency, narrowband in the infrared, and polarization sensitive. Since then, they've rapidly improved such that individual metalenses can achieve efficiencies of greater than 90%, Na greater than 1.48. Some are broadband in the visible, polarization insensitive, or have diameters greater than 2 centimeters. However, there's no individual metalens that can achieve all of the above, which are all important aspects of a lens used in imaging systems. However, once there is a metalens that can achieve all that, we'll be able to replace the typical lenses in a system such as this with metalenses. And that would reduce the overall length of the system by getting rid of the excess thickness of the lens. So the majority of this system, however, is taken up by the propagation distance of the light. And so we would want a plate that we can insert into the system to reduce the propagation distance. And we call a device that does that a spaceplate. So the general idea for this is that for a ray of light incoming at an angle theta, propagating over a distance d effective, we would be able to take that propagation distance and compress it into a smaller distance d, which is the thickness of the spaceplate. Now, two important features that are retained are the lateral translation w and the incident and outgoing angle theta. And that second point is one of the major things that differentiates this from something like a lens. And the way we quantify the effectiveness of the spaceplate is that we define a compression factor R, which is equal to d effective over d. So one of the ways that we can apply the spaceplate is in a camera. So if we insert a spaceplate in between the lens and the sensor of a camera, it reduces the propagation distance, and therefore we can reduce the length of the lens barrel. If we use it in conjunction with a metalens, we can further reduce the length of the system and have it perfectly monolithic. So this can be applied to telescopic lenses or telescopes, as well as eliminate the camera bump on the back of your phone by creating an ultra-thin flat camera. Other applications include spectrometers, solar collectors, and basically any other optical system that requires the free propagation of light. So how do we go about designing a spaceplate? Well, imagine that we have a collimated beam incident on a lens, which focuses the beam at a distance f away, creating the focal plane. If we insert a glass plate into the system, where the glass plate has an index of refraction greater than that of the surrounding medium, how do we think the focal plane will move? Well, if we follow through Snell's law, the beam will bend towards the normal, and the focus plane shifts further away from the lens than it did without the glass plate. So this is the exact opposite of what we are looking for in a spaceplate. So it's in essence has expanded the system, and in addition, it's added aberrations. So for example, in a microscope objective, this one compensates for the aberrations created by a 0.17 millimeter microscope cover slip. So what if we do the exact opposite? What if we insert a plate with an index of refraction less than that of the background medium? Well, we'll see that the focal plane gets shifted towards the lens, and that demonstrates that this is a kind of spaceplate, which we call a low-index spaceplate. Now, the compression factor for this is the index of the background medium divided by the index of the plate. However, you still get aberrations for large Na, and your total range of angles is restricted by the critical angle for total internal reflection. Now, for the purposes of most imaging systems, the background medium is air, so therefore we would need an index of refraction less than 1. Luckily, there are materials like this called ENZ materials. However, they're prohibitively lossy to be used in imaging systems right now, but just like metalenses, they're improving very rapidly. So for the purposes of this experiment, we're going to use a background medium of an index greater than 1. Now, if we want to find other spaceplate designs, we need to look to Fourier optics, which states that any field distribution can be represented as the sum of plane waves. And in addition, any optical component can be described by its action on each of these plane waves. Therefore, we need to consider how free space over a distance d effective will transmit and shift the phase of each component, and then have our spaceplate replicate that. So luckily for any plate, the momentum is conserved along the interface, which we're defining to be the xy plane, and therefore the phase accumulation is automatically equal to that of free space. So we only need to engineer the z component of our phase accumulation, which is given in this equation. And so we just need to get our spaceplate to replicate this phase accumulation. Since the phase accumulation is a function of angle, that necessitates an angle-dependent refractive index. And the solutions to that are plotted here, the index of refraction as a function of the k-vector angle within the spaceplate in radians. And all of these curves represent a compression factor of 10. Now the green curve here represents a low-index spaceplate, where the index of the plate is less than that of the surrounding medium. And the red curve here is a new kind of spaceplate, which is a negative uniaxial crystal with its optic axis perpendicular to the interface. Now, a negative uniaxial crystal is a birefringent crystal with the ordinary index NO greater than the extraordinary index NE. And so I'll go into a bit more detail about this kind of spaceplate, which we call a uniaxial spaceplate. The compression factor is NO over NE, and like I said, the optic axis has to be normal to the interface, and there are no aberrations at any angle for this kind of spaceplate. In addition, we choose a background medium similar to that of NE so that we eliminate any contribution from Snell's law. So how are we going to test out this kind of spaceplate? Well, we're going to have an object which is imaged through a lens and forms an image plane on the other side. Then with the insertion of the uniaxial spaceplate, we should observe the image plane shift by a distance delta less than 0. It is negative because it's going against the direction of propagation. Now we use calcite as our spaceplate because it has the largest difference between its two indices of refraction, thus giving us the best compression factor. And we use glycerol as our background medium because it has an index of refraction roughly that of Ne. Now we expect an image plane shift of 3.5 millimeters against the direction of propagation. So let's see what happens. We will translate a camera through the image plane, and we should observe the image formed by the calcite through the calcite first, and then we should see the image formed through just the background medium from a separate trial. So here we observe the image formed through the calcite, and then the image formed through just the background medium as the camera is translated back. So therefore, we observe the image formed through the calcite come into focus first, and then the image formed through the glycerol further away. Now, this only works with E-polarized light, so we had to prepare the polarization beforehand. And here are some select screenshots from that video you saw. As you see, the image formed through just the background medium of the glycerol, its position is defined as z equals 0. And then once we add the calcite, we observe the image plane shift by 3.4 millimeters against the direction of propagation. And so this agrees fairly well with our expected value of 3.5 millimeters. A more accurate way of looking at the shift would be to look at how a beam comes into focus rather than how an image comes into focus. So as you can see from these beam profiles plotted as a function of propagation distance, the beam through just the background medium, its waist is defined to be at z equals 0. And then with the insertion of either the low-index spaceplate or the uniaxial spaceplate, we observe a shift in the focus against the direction of propagation, thus showing that we have replaced space in our spaceplate. Unfortunately, I don't have time to go through all these details here, but the important point is that our measured shift is very similar to our predicted shift for both cases. Now, if we want to compare the aberrations caused by both of these spaceplates, we can look at walk-off, which is related to our value W, which I mentioned earlier. Now, we see that the beam will shift in the transverse direction as a function of incident angle, and the ideal cases are shown with these dotted and dashed lines. So for the low-index spaceplate, we observe significant deviation from the ideal case as it approaches the critical angle 42 degrees. And with the calcite plate, the uniaxial spaceplate, we observe no deviation from the ideal walk-off for any angle, and therefore we can conclude that the airplate has aberrations for large incident angle, while the calcite plate has no aberrations regardless of angle. So the last spaceplate that I'll talk about is called a multi-layer spaceplate. It is a monolithic slab of 2 or more materials that aims to replicate the same phase accumulation of the other spaceplates. It's possible to achieve much higher compression factors with this type of spaceplate, and it doesn't follow the same general solution as I detailed earlier. Now, we use a genetic algorithm to generate this multi-layer design, and our most recent design has 25 layers of alternating silicon and silica of varying thicknesses. And the overall thickness of the device is 10 microns, and we observe in simulation a 43 micron shift. And this is for a wavelength of 1540 nanometers in the infrared. And it gives us a compression factor of 5.2, which is quite a bit higher than the compression factors of less than 2 from the other types of spaceplates. And it's important to note that this works for both P and S polarizations. To conclude, I'll just summarize. We have introduced the concept of a spaceplate, which reproduces the Fourier transfer function of free space, which is greater than the thickness of the spaceplate. We demonstrated 2 proof-of-principle designs for a homogeneous spaceplate. We are developing multi-layer designs with much larger compression factors. And finally, when combined with metalenses, spaceplates can compactify optical systems, including imaging systems. So if you're interested in learning more, you can look at our paper on arXiv. And yeah, thank you very much for watching.